Hello everybody. In this video we're looking at AICE Physics, syllabus code 9702. This is paper 22 from October-November 2018. Question number 4, dealing with waves. This worked example specifically deals with amplitude, phase difference. The question begins, sound waves are longitudinal waves. By reference to the direction of propagation of energy, state what is meant by a longitudinal wave. Well, this is very clearly related to the learning outcome to be able to describe both transverse and longitudinal waves. You should know the definition of this. Take a moment to see if that isn't forthcoming. That's right. If you said, well, a longitudinal wave has particles that move along the length of the wave, in other words, the wave is propagating, there's the direction of propagation of energy, and the particles are moving along the length or parallel to that direction of propagation of energy. That's what characterizes a longitudinal wave. So state what is meant by a longitudinal wave. We can say a longitudinal wave has particles oscillating parallel to the direction of propagation of energy. Keywords there: longitudinal, parallel, transverse, remember, are perpendicular. The question goes on to read, a stationary sound wave in air has amplitude A. In an experiment, a detector is used to determine A squared. The variation of A squared with distance x along the wave is shown in figure 4.1. State the phase difference between the vibrations of an air particle at x equals 25 centimeters and the vibrations of an air particle at x equals 50 centimeters. Now, this is a pretty tricky question because we've got to remember that intensity is proportional to amplitude squared. So our detector is able to determine amplitude squared, and we see a plot of amplitude squared against x. So if we're looking at an air particle at x equals 25, well, that corresponds to this peak right here. If we then go over to x equals 50, we say, oh, well, that's the next peak. And when we're used to sort of looking at waveforms, we think about, well, the phase difference between two identical points is, 0 degrees or 360 degrees. But we've got to remember that we're looking at a plot of A squared here. And so if we think about like this wave beginning at this peak and then it reaches, 0 arbitrary units of amplitude squared, well, really the wave would continue to decrease. In other words, there would be a negative displacement, okay? But we're plotting amplitude squared, and so when we square that negative value, it puts it back up here to the positive. And so really the waveform would continue dropping below 0 here to the negative displacement and then back up to equilibrium, and this would actually be the next identical point, sort of 2 crests away when we're looking at a plot of A squared. And so that's the key idea that many students are not going to be mindful of when they're looking at 25 and 50. We've got to sort of think about this as that, this point here would continue to drop below, or that this point here was already sort of below here. And so when you're looking at points where sort of one is at a trough and one is at a crest, those points are at a phase difference. They're half a wave away, or 180 degrees out of the 360 total degrees. And so that the correct answer here is 180 degrees, because a particle at 25 and 50 are actually sort of separated while on a plot of A squared, just sort of 1 peak away. They would really be half a wave off from each other. Remember, when we square that negative displacement, it moves it back up here to the positive axis. So that's the key idea. It says the speed of the wave in the air is 330 meters per second. Determine the frequency of the sound wave. So if we know the velocity is equal to lambda, the wavelength, times f, the frequency, and we wanted to determine the frequency of the wave, then we can kind of use a similar idea that, if the wave starts here and this is the crest, remember that while this sort of looks like a crest, it would really be at the negative displacement, and so the wave really repeats again right here. So the wavelength here is actually 50 centimeters. So we can write that the frequency is equal to the velocity divided by the wavelength. We're given the velocity, the speed of sound in air, 330 meters per second. The wavelength we just deduced was 50 centimeters. So we can just convert the prefix centi to 10 to the negative 2. We can see that meters are going to cancel, and we're left with units of reciprocal seconds, which is the same thing as hertz of frequency. So our calculation is 330 divided by 50 times 10 raised to the negative 2. 10 to the negative 2 is centi, equals 660 hertz. Lastly, we're asked to determine the ratio of the amplitude A of the wave at 20 and the amplitude A of the wave at x equals to 25. And so it looks like at 20, the amplitude squared is 2.2468. So it looks like it's crossing right there at about 2.6. So the amplitude would be the square root of 2.6, right? Because we're looking at a plot of amplitude squared. So the amplitude of the wave at x equals 25, that's this point here, is all the way up to 4, and so we'd be looking at the square root of 4. 2.6 over 4, and then the square root of that, 0.80.